Hi Year 5, today we will be touching on the topic of 4.3 wave characteristics. Please turn your textbook to page 135. So we start off with something very basic. What is a wave front? Now before we talk about wave front, let's talk about how do we even draw a ray. So a ray, you know, you use a straight line with an arrow to represent it. So how do you draw a wave front? A wave front is drawn by, it's always 90 degrees to the ray. So these black lines here are all called wave fronts. They are always equidistant from each other. Okay, and if I add in the wave, you can see that basically they coincide with the peaks of a ripple or wave. And the distance between each wave front is one wavelength. So the direction of the ray tells us the direction of energy transfer. Now on page 135 of your textbook, you can see this diagram. And this is basically a ripple tank where you have a vibrator creating waves from one end, and the wave will move towards the other end. And at the bottom of the ripple tank, you will be able to see the wave pattern on the screen. So you'll be able to see white lines or bright spots, bright lines. Now this is very much like when you go swimming, and when you're swimming, you look under the pool. On the floor of the pool, you will be able to see bright lines that are constantly moving, right? So those bright lines that you're seeing on the floor are the wave fronts. So let's look at this video of a ripple tank. You can see that there are ripples on the top, and at the bottom, the white lines that you see, these are the wave fronts. So you can see that the distance between each white line or bright line is about the same, and these are all our one wavelength apart, and each of these bright lines here are called the wave fronts. Okay. Now we move on to something that's very simple that you've already learned in IGCSE. You know that angle of incidence equals angle of reflection when reflection of a wave takes place. So if I have a reflective surface, I have my incident ray, I have my reflected ray, and if I draw in my normal in dotted lines, which is 90 degrees to the surface, the angle of incidence is equal to angle of reflection. Now if I draw this out in terms of wave front, this is how it will look like. So basically, remember, our wave fronts are 90 degrees to the ray. If I were to draw in my normal, you can see that my reflected ray will be 90 degrees. Will be the angle of incidence equals to angle of reflection, and my wave fronts are 90 degrees to the reflected ray. So what if I have a spherical wave? Basically, you can see that same thing. Okay, now whether it's straight wave front or a spherical wave front, during reflection, the frequency doesn't change, the wavelength doesn't change. So look at this distance here. This wavelength doesn't change. Same thing. This is my incident wave, right? This is my reflected wave. You can see that the wavelength doesn't change, but the direction of the wave changes. So this is on page 136 of your textbook. You will be able to see the diagram of the wavefront on the top left-hand corner. And then if you go down to the bottom of the page, you can see these three paragraphs, right? The top paragraph, please highlight there is no change in wavelength during reflection. And write down that the frequency also doesn't change, only the direction changes. Now for refraction, what happens during refraction? So if I have this wave that is traveling from a deeper part of the pool to a shallower part of the pool, it is similar to how light travels from a less dense medium to a denser medium. So how do I do that? Again, you can see the wavefront, right? So we just have to draw in the ray, which is 90 degrees to the wavefront. Draw in your normal, which is 90 degrees to the boundary. Draw in the straight through ray for comparison in dotted lines. And then you know that when your light travels from an optically less dense medium to an optically denser medium, it bends towards the normal. So we draw the ray bending towards the normal. Now, how do I know that when it's traveling from a deeper end of the pool to a shallower end of the pool, the wave will also move, the ray will bend towards the normal? you should have learned this in IGCSE, but how I do it is I liken it to people walking through a door. When it's a deeper end of the pool, it's as if my door is big. So this is my door, big door, and then I have people walking through it. When you have a big door, people can go through it at a faster speed. But when you have a small door, when people want to walk through it, the speed will be lower. Right, the speed going through the door will be lower. So it's the same thing. When light travels from an optically less dense medium, speed is faster. When light travels in a denser medium, the speed is slower. Which is the same as when waves travels in a deeper pool, the speed is faster. When waves travel in a shallower pool, the speed is slower. Now, based on what we can see from the wavefront, you can see that the wavelength in the deeper pool compared to the wavelength in the shallower pool is larger. So when it goes to a shallower pool, the wavelength will change, the speed will change, but the frequency in the period does not change. Now, why is it the frequency doesn't change? Frequency doesn't change because the source is the same. Whenever the source is the same, we mentioned before that the frequency will not change. And since frequency equals to 1 over period, if frequency doesn't change, the period doesn't change. Try this out now. Pause here, use a pencil, use a ruler to draw out the refracted wavefronts and then label the wavelength. Now, use pencil please, so that if it's wrong, you can always erase it later on. Now, if you don't know how to do it, then you just do it together with me now. So, number 1, you have your ruler. You bring your ruler 90 degrees to the boundary. Draw in your normal in dotted lines. So, this is the normal. Next, you draw in your incident ray. So incident ray is always 90 degrees to the wavefront. Now I've chosen to draw using this wavefront. You can choose to draw for any wavefront. So everything I'm going to start would be draw from would be from this wavefront here. Okay, the first wavefront on the right. I'm also going to draw in my straight through ray in dotted lines for comparison. Then I know that when say light travels from air to an optically less dense medium to an optically denser medium, it's going to bend towards the normal. So I use my ruler, it will bend towards the normal. So what do we do after that? Since this is, I draw my new wavefront. My wavefront must be 90 degrees to the ray. So notice that this is 90 degrees. So this is my new wavefront. And then all my subsequent wavefronts, now I connect it to the incoming wavefront. Okay, so I connected to this wavefront here. This one was connected to this wavefront here. And my new wavefronts must be parallel to each other. So the third wavefront connected, and then it must be parallel to the previous two wavefronts, and then the same thing. The last wavefront parallel to the previous three wavefronts. And you notice that this refracted ray is 90 degrees to all my wavefronts. Now we go on to diffraction. What's diffraction? If you go to page 136 of your textbook and your notes, you can see that when you have waves coming in and it passes through a little gap, it gets diffracted. Diffracted means the wave spreads out. Alright, so the gap, I'm going to call that distance B. And you can see that the wavelength before diffraction and the wavelength after diffraction is the same. Now, as the gap B gets bigger, so as the distance of the gap gets bigger, you can see that the effects of diffraction gets less obvious. It becomes straighter and straighter. So in order for diffraction to occur, meaning in order for it to become very curved, very bent, in order for your wave to bend a lot, your wavelength must be about the same or smaller than the gap, the distance of the length of the gap. Now pause here and try example 1. So for example 1, they tell us that a water wave is entering a harbor and it passes from deep to shallow waters. In the deep end, it has frequency f1 and speed f1. In the shallow end, it has frequency f2, speed v2. Sorry, frequency f2 and speed v2. They ask us to compare the frequency and the speed between the deep end and the shallow end. Now, straight away you should know that since it's the same wave, came from the same source, the frequency should remain constant. What about for the speeds? You need to know that, you just need to recall that in deeper end is like walking through a bigger door. Bigger door means it's faster. Shallow end means like walking through a small door. A narrower door means the speed is slower. So, So V1 is greater than V2. Answer A. Now we go to example 2. Pause here and try this out first. So example 2 tells us that we have this solid wall, high wall that separates two gardens X and Y. So this is my wall. Music from a loudspeaker in X. So we have this loudspeaker here. Okay, that emits sound in all directions. Can be heard in Y even though X cannot be seen from Y. Now, how can you hear this? Is it by absorption? Now, if the wall absorbs the sound, then of course Y can't hear it, so no. Answer is by diffraction. Diffraction means the sound can bend, right? Is it by reflection? So if the sound waves comes this way, it's going to get reflected. If the sound comes this way, it's going to get reflected this way. So if it gets reflected, Y wouldn't be able to hear it. So it's not by reflection. By refraction, now refraction means it should it changes direction, right? But then it's usually from optically less dense to optically denser medium, or from optically denser medium to optically less dense medium. In this case here, the air is one medium, so no. Okay, so it's by diffraction. Moving on page 137, so this is on page 137 of your textbook. We want to find out what's the relationship between the energy of a source and its amplitude. Now you know that the loudness of a sound or the brightness of a light depends on the amount of energy that is received by the observer. So in order to make a filament lamp glow brighter, we will need more electrical energy. So we know that energy is then proportional to amplitude, but in this case it's going to be proportional to amplitude squared. Alright, now how do I prove this? From what we have learned in topic 4.1 and 2.2, we know that springs have got energy of E equals to half K x naught square. Now what's x naught square? If you have your graph out, x naught is going to be the amplitude of the spring, right? So we know that springs perform simple harmonic motion, which results in a sinusoidal wave graph, and therefore we can equate the energy of springs to a wave. And since half kx is a constant, this tells me that energy is proportional to a squared, all right, where x naught is our amplitude and a is the amplitude. So E is proportional to a squared, the amplitude square. Now since energy is equal to power times time, and I can then equate that power is proportional to amplitude square. Okay, so if I picture waves being emitted from a point source S and it spreads out in all directions, this means that energy will be spread increasingly thinly the further we go from the source. So if you look at this diagram here, the further out you go, the energy is spread out a bit more, right? It's spread out more thinly. To make intensity, now we're going to talk about intensity. To make intensity comparisons more straightforward, I'm going to use the idea of energy transferred per second. Energy per second, what is that? E over T, that is power, isn't it? So power of the source. So I'm going to relate intensity with power, and intensity equals to power over area. This is surface area of the sphere at that radius. So I'm talking about the surface area, this surface area over here. And therefore, the formula would be then intensity equals to power over 4 pi r squared. Now, if my power is constant, because power from the source is a constant value, as my radius changes, okay, so what happens to intensity? You can see that the intensity is proportional to 1 over r squared. So this shows us that intensity is an inverse square relationship with the distance from a point source. Now, you have all experienced this before, that when you're sitting near a campfire, you feel the intense heat from the fire. However, the further you go from the fire, the intensity of the heat that you feel decreases. And now you know that what you feel decreases by square of your distance. SI unit for intensity is watts per meter square. So power is watts, right? Area is meter square, so watts per meter square. Now, what's the relationship between the amplitude of the source's energy to the intensity where you're at? So we already know that energy is proportional to A square. We also know that intensity is equal to power over 4 pi r square. And since E equals to PT, E equals to PT, let's start from here. Okay, so since E equals to PT, we know that power is proportional to A squared. Now, when you have I equals to P over 4 pi r square, and at a constant distance away from the source, meaning R is constant. So if R is constant, 4 pi r is constant, this tells me that, so these are all constants, right? This tells me that I is proportional to P. And since P is proportional to A square, so I is proportional to P is proportional to A square, this tells me that I is proportional to A square. Now this formula can be found, or this relationship can be found in your data booklet. Same thing for I proportional to 1 over R square. Just that in your data booklet, they say it's proportional to 1 over X square. So this X here just means the distance from the source. Pause here and try example 3. So example 3 tells us that we have 200 watts speaker, projects a sound in a spherical wave, find the intensity of the sound. So I want to find the intensity. So this is I, this is P, at a distance of 1 meter and 2 meters. So this is R away from the speaker. So using the formula I equals to power over area, I equals to P over 4 pi r square. We know that P is 200, and at R equals to 1, I substitute my R equals to 1 in here. You get I equals to 16 watts per meter square. Now, at 2 meters, so using the same formula, I substitute 2 in for my distance. You get 4 watts per meter square. From this, you can see that by doubling the distance, your intensity reduces by 75%. It reduces by to a quarter of it, isn't it? Okay, pause here and try example 4. So, for example 4, they tell us that at distance of 18.5 meters from a sound source, the intensity is 2 times 10 to the power minus 1 watts per meter square. I want to find the intensity at distance of 26.5 meters, and I want to compare the amplitudes of the sound at 18.5 meters and 26.5 meters. So what do we do here? Did you get the answers? These two answers. If you did, you can move on. So for part A, I use the formula I equals to P over 4 pi r square. I know that this is my R. I know that this is my I. So I want to find P first. So I substitute R and I in. I can find that P is 860.168 watts. Now at 26.5 meters, the intensity equals to power. Power being this value divided by 4 pi. This is my new R square. So you get 0.0975 watts per meter square. Now how do I compare the amplitudes of the sound? So you know that the intensity is proportional to amplitude square. I've already found intensity at, this is the intensity at 18.5 meters. This is the intensity at 26.5 meters. I'm call that I1 and I2. I want to compare amplitudes, right? So I'm going to make it such that amplitude is proportional to square root of I. Basically, I'm square rooting both sides. Okay, so A1 is proportional to 2 times 10 to the power minus 1, and square root of that. And A2 is proportional to square root of 0.0975. Then I take A1 divided by A2, which will get you 1.43. So this tells you that A1 is 1.43, the amplitude of A1 is 1.43 times greater than A2. Moving on, what is superposition? So let's turn to page 139 of our textbook. Let's highlight this. The first line, when you have two or more waves meeting at a point, the resultant displacement of the wave is going to be the vector sum of the individual waves. So highlight this on your textbook, the first two lines of the top paragraph. Now, what does this mean? We'll talk about it later on. I'll show you what it means. Now, superposition can also be called interference. Later on in topic 4.4, you'll learn that interference can be constructive or destructive or anything in between. So we'll learn about these terms later on, all right? So what is superposition? Now, if I have two waves and they're moving towards each other, each of these waves has got amplitude A. When they meet at a point, the resultant wave will have amplitude of 2A. So remember I said that the total displacement is a vector sum. So I'm adding that individual displacements together. Now what happens after that? The right wave 1 will move on to the right and wave 2 will move on to the left, and they'll have their individual original amplitudes of A. So what if I have two waves of different amplitudes? It's the same thing. Initially, I have amplitude of 3A wave on the left-hand side moving to the right, and on the right-hand side, I have amplitude of 2A in the opposite direction moving to the left. Now, when they meet a point, the resultant displacement, right, will be 3A plus minus 2A, because if I take upwards as positive, so this is going to be a negative 2A, I need to add them up together, so I get resultant of A upwards. Then what happens after that? My amplitude of 3A wave will continue to the right, my amplitude of 2A wave will continue to the left. Now what's the intensity of the pulse on the left? What's the intensity of this pulse here? So remember we said that intensity is proportional to A square. So the intensity of that would be 9A square, proportional to 9A square. Right? Because I proportional to A square, so I proportional to, in this case, it will be 3A square. So it will be 9A square. Now try this out. What will the resultant wave look like? Pause here and draw it using pencil, please. So what will happen is that this will add up with this on the left hand side. So you end up getting, if I call this A, I end up getting 2A. This side here adds up to this side here. So over here will be 0 plus 0 ends up here, right? And then what will happen is that, let's talk about the middle part. This middle part here, I have A plus over here. So if this is A, this part here will be half A plus half A, 1.5 A, right? So in the center here, this is 1.5 A. So what you get? This point. What about over here? Over here will be 1/4 A. Over here is still 1A. So 1A plus 1/4 A will be 1 and 1/4 A. So that will be at this point here. Oh, apologies. Over here is 1A. Alright, so this will be it. So you end up getting something like this. Yeah. Okay, so over here, let me delete that. You can always add this point here also and this point here. So this is 1A. Over here would be 3/4 A. So 1 plus 3/4 A, 1 and 3/4 A. So somewhere here. So this is how your resultant wave will look like. Okay, then try this out here now. So again, I start off like this. Now, this point here plus this point here, what do I get? Now, say if I call this A, same thing. It's the same height, right? So this is A. What's going to happen? We will have A plus 0, so we end up getting A still. Okay, then at this point here, this is half A. Over here, this is also half A, so we end up getting A. oops, sorry, somewhere here, A. Okay, and then at this point here, this is 0, but here this is A, right? So 0 plus A. So we end up getting a straight line like that. Now what happens after the two waves have passed? After the two waves have passed, you would get something like this, where your wave 1 will end up going to the right, wave 2 will end up moving to the left. Pause here and try example 5. So for example 5, we have two wave pulses, each of amplitude A approaching each other. They then impose before continuing in their original directions. What is the total amplitude during superposition? So total amplitude during superposition and the amplitude after superposition. Now, during superposition, you know that it's the vector sum, right? So it's just A plus A. And since both are in the positive direction, during superposition will be 2A. What would be the individual amplitudes after superposition? It's going to move on and they retain their individual amplitudes as before. So it just be A. So answer D. Now try example 6. Pause here. So we have two waves that are moving towards each other as shown in the diagram. What is a possible combination of the two waves after a short time? Now I don't know which time I'm talking about, whether we're talking about at the end or at the start when they start to superimpose, but let's look at what's possible. So when I have these two added together at the same time, I know that this is plus 2, this is minus 3. I end up getting a minus 1. So C is definitely out. I know that D is also definitely out. There's no way I can get a minus 4. Now let's look at A and B, which is possible. So if it is at this point here, where your wave on the left is coming into the right, what's going to happen is that I will still have 3 on the left. Okay, so maybe not possible because I have nothing that's on the left that's downwards. So maybe not this way, but more of, say if it has already moved like that. So I have 3 on the right at the bottom. So I have 3 on the right at the bottom, 3 on the right at the bottom. What's going to happen next? At this point here, you can see that it's a plus 2 minus 3. So I'm now getting a minus 1, right? So we end up getting a minus 1. And then over here, there is no superposition. So it's just like this. So it looks like this, isn't it? Where you have minus 1 and then a positive 2 at the top. So A is possible. Now what about for B? Now B, you can see that they have directly superimposed. So if they're directly superimposed, it means that it should be a bottom minus 1. So B is also out. So it's A. Okay, we're going to stop here for today. Please do the questions that are given in